How big is the universe? At first glance, the question sounds simple, the kind of thing a child might ask while staring up at the night sky. But hidden behind that simplicity is one of the most mind-bending stories in science, and an honest answer to it can permanently change the way you see the world. Today, we're climbing a ladder of cosmic scales, from our own planet to the farthest edges of existence. With every step, the numbers will get more absurd, familiar units of measurement will become useless, and our home will shrink smaller and smaller. Fair warning, by the end of this journey, the word huge is going to sound pathetically weak. So let's start from the very beginning. But before we launch, let's glance back at how humanity's picture of the world's size has evolved over time. For ancient civilizations, the entire universe fit under a dome of sky, with stars seemingly nailed to it, practically within arm's reach of the nearest hill. The ancient Greeks made the first real breakthrough. Eratosthenes calculated Earth's circumference by comparing shadows in 2 different cities, while Aristarchus of Samos estimated the distances to the moon and sun, realizing for the first time just how monstrously far away and enormous the sun really was. For centuries after that, the universe ended at a sphere of fixed stars just beyond Saturn's orbit. Copernicus expanded the picture by removing Earth from the center. Herschel stretched it out to the scale of the Milky Way. And it was only about 100 years ago that humanity discovered even our galaxy isn't the edge. Every generation of astronomers was convinced they were finally seeing almost everything. And every single time, the universe turned out to be immeasurably bigger than they thought. Keep that pattern in mind. It comes back around by the end of this story. Let's start with something familiar. Earth. Our planet's circumference is about 40,000 kilometers. A modern passenger jet could circle it non-stop in roughly 2 days. For a human being, that's an enormous distance. Most of us won't walk even a fraction of it on foot in an entire lifetime. Hold on to that feeling of Earth's vastness. We're about to start ruthlessly demolishing it. Already the distance to the moon, about 384,000 kilometers, is nearly 10 times Earth's circumference. Every other planet in the solar system lined up end to end would fit inside that gap. And the moon is our closest cosmic neighbor, the only celestial body a human being has ever set foot on. Let's climb one more step, to the sun. It sits about 150 million kilometers away. That distance matters so much to astronomy that it earned its own name, the astronomical unit. Light, the fastest thing in the universe, covers it in 8 minutes and 20 seconds. In other words, when you look at the sun, you're always seeing it as it looked 8 minutes ago. A passenger jet would need roughly 20 years of nonstop flight to make that trip. The sun itself is staggering too. About 1,300,000 Earth-sized planets could fit inside it, and it accounts for 99.86% of the entire solar system's mass. Every planet, including giant Jupiter, is just crumbs off the sun's table. So how big is the solar system itself? Neptune, the farthest planet, orbits about 30 astronomical units from the sun. Light takes more than 4 hours to get there. But the system doesn't end with the planets. Beyond Neptune lies the Kuiper Belt, home to Pluto and thousands of icy bodies. And beyond that, the enormous Oort cloud, a spherical reservoir of trillions of comet nuclei, estimated to stretch nearly a full light year from the sun. To grasp the scale, humanity's fastest spacecraft, the Voyagers, launched almost 50 years ago, won't leave the Oort cloud for tens of thousands of years. We launched them within one generation's lifetime, but they'll cross the true edge of our home system only after hundreds of generations have come and gone. To visualize our system's proportions, let's build a scale model. Say the sun is a soccer ball sitting in the middle of a city. Earth would be a pea 23 meters away, Jupiter a ping pong ball 120 meters out, Neptune a pea 700 meters away at the far end of the park. So where does the nearest star land in this model? Brace yourself. You'd need to place a second soccer ball 6,000 kilometers away on another continent. Between the 2 balls, a handful of peas scattered around each one, and thousands of kilometers of absolute emptiness. That's an honest portrait of space at scale. So the next time you see a pretty diagram of the solar system with the planets tightly clustered near the sun, remember, real proportions are simply impossible to show on paper. At true scale, a single sheet of paper would only fit the sun. The planets would have to be drawn in the buildings next door. Here we need to switch rulers. Kilometers stop being useful. Meet the light year, the main unit of cosmic distance. It's the distance light travels in 1 year, about 9.5 trillion kilometers. Worth stressing, a light year measures distance, not time, even though time is quietly baked into it. Looking at an object 100 light years away means you're seeing it as it was a century ago. Telescopes are time machines, and the farther we look, the deeper into the past we're peering. Hold on to that thought. It pays off in the most unexpected way by the end of this journey. Now for our first interstellar step. The closest star to the sun, the red dwarf Proxima Centauri, sits 4.2 light years away. Doesn't sound like much? Let's convert. That's about 40 trillion kilometers. Shrink the sun down to the size of an orange, and Earth becomes a grain of sand 10 meters away, while Proxima Centauri becomes another orange 3,000 kilometers away, on the far side of the continent. Between them, almost nothing, but the occasional stray hydrogen atom. And that's the real truth about space. It's not made of stars, it's made of the staggering emptiness between them. Even our fastest existing spacecraft would take tens of thousands of years to reach Proxima. That emptiness is the main obstacle to interstellar travel, and the main reason even a radio conversation with hypothetical neighbors there would stretch across decades. The question takes 4 years to arrive. The answer, another 4 to come back. Interestingly, an Earth-sized planet has been found in Proxima Centauri's habitable zone, a potentially livable world orbiting literally the nearest star to us. If humanity ever does set out for the stars, we already know the first address. The next rung on the ladder is our own galaxy, the Milky Way. It's a giant spiral disk of stars, home to somewhere between 200 and 400 billion of them. Its diameter is about 100,000 light years, 100,000 years for light, just to cross it from edge to edge. By the time a photon that left one side of the galaxy reaches the other, the entire history of human civilization on Earth could play out, more than once. Our sun and its planets sit in a quiet outer suburb, roughly 26,000 light years from the galactic center, completing one full orbit around it every 230 million years. The last time we were at this exact point in our orbit, the first dinosaurs were just beginning to walk the Earth. And even the galaxy's apparent size is deceptive. The visible star disk is just the core of a far larger structure. The Milky Way is wrapped in an enormous halo of dark matter, an invisible substance that neither glows nor absorbs light, but gives itself away through gravity. It's what keeps that galaxy's rapidly spinning outer edges from flying apart. This halo stretches hundreds of thousands of light years beyond the visible disk and outweighs all the stars combined, many times over. Which means that even the majestic panorama of the Milky Way we see in the night sky is only the smaller glowing tip of the iceberg. Most of our galactic home stays permanently hidden from view. According to current data, ordinary matter, the stuff we, the stars, and the planets are made of, accounts for only about 5% of everything in the universe. The rest is split between dark matter and the even more mysterious dark energy. So as we measure the size of the universe, it's worth remembering. We're mapping a world that's 95% invisible. To really feel the number 400 billion stars, try this thought experiment. Start counting stars 1 per second, no sleep, no breaks. Counting every star in the Milky Way would take you more than 12,000 years. And now brace yourself. There are more galaxies in the universe than there are stars in our galaxy. But let's not get ahead of ourselves. We're climbing this ladder one rung at a time. For a long time, humanity believed the Milky Way was the entire universe. Those hazy smudges in the sky were assumed to be just clouds of gas within our own galaxy. Everything changed in 1923, when American astronomer Edwin Hubble picked out individual stars inside the Andromeda Nebula and used them to calculate its distance. The result shook the scientific world. The nebula wasn't a cloud at all. It was an entire separate galaxy, millions of light years away. In a single day, the known universe grew 1,000-fold. Today, we know Andromeda is our closest major neighbor, 2.5 million light years away. The light you see when you look at it on an autumn night set out on its journey before modern humans even existed on Earth. This is a good moment to answer a fair question. How do astronomers actually know all these distances? You can't exactly stretch a tape measure to a star. The answer is the cosmic distance ladder, one of the most elegant constructions in all of science, where each rung leans on the one below it. The first rung is parallax. Nearby stars shift slightly against the background of more distant ones as Earth moves from one side of its orbit to the other, and that shift lets us calculate distance. Pure geometry, school-level trigonometry, applied at cosmic scale. The Gaia Space Telescope used this method to measure distances to nearly 2 billion stars. The second rung is Cepheid variables, pulsating beacon stars whose blinking period is tightly tied to their true brightness. Knowing how bright a Cepheid should be and seeing how dim it actually appears gives us its distance. That's exactly how Hubble measured the distance to Andromeda. The third rung is a certain type of supernova that always explodes with the same power. These standard candles are visible across half the universe. Step by step, rung by rung, humanity has stretched its ruler all the way out to the horizon of the cosmos. The Milky Way and Andromeda, together with about 50 smaller galaxies, form the local group, our galactic neighborhood roughly 10 million light years across. But even that's a tiny crumb. The local group belongs to the Virgo supercluster, which in turn is part of a truly colossal structure called Laniakea, Hawaiian for immeasurable heaven. Laniakea contains about 100,000 galaxies and spans 520 million light years. And even that isn't the limit. At the largest scales, galaxies arrange themselves into what's called the cosmic web, a network of filaments and sheets woven from millions of galaxies, separated by gigantic empty regions called voids, hundreds of millions of light years across. At this level, the universe looks almost like foam or a neural network. Matter forms only thin films along the edges of enormous bubbles of emptiness. Within the strands of the cosmic web, astronomers have found structures so large the imagination simply gives up. The Hercules Corona Borealis Great Wall, a colossal cluster of galaxies, is estimated to stretch across 10 billion light years, more than a tenth of the entire observable universe. The existence of structures this colossal is actually a point of scientific debate. The basic principle of cosmology holds that, at the largest scales, the universe should be uniform, with no dominant superstructures. And findings like this force scientists to double-check both the observations and the theory. That principle of uniformity, by the way, is one of the pillars of modern cosmology. No matter where you look or where you stand, at scales of hundreds of millions of light years, the cosmos looks the same everywhere. The universe has no center and no edge. Every point is equally valid, and an observer in any galaxy sees roughly the same view we do. And now we've reached the final rung of the ladder, the observable universe. Here waits the most fascinating and most paradoxical number of all. The logic seems simple enough. The universe is 13.8 billion years old, so surely we can only see objects up to 13.8 billion light years away. Light simply hasn't had time to travel any farther. But reality is trickier than that. While that ancient light spent billions of years traveling toward us, the space of the universe itself kept expanding, carrying the galaxies that emitted it farther and farther away, like dots on an inflating balloon. As a result, the objects whose light we're catching today are now much farther away than they were at the moment they emitted that light. Accounting for this expansion, the observable universe has a radius of about 46.5 billion light years, and a full diameter of roughly 93 billion light years. 93 billion light years, a number that's nearly impossible to grasp. Let's at least try to get closer to it. Current estimates suggest this volume contains around 2 trillion galaxies, averaging about 100 billion stars each. Multiply that out, and you get a mind-melting total. There are more stars in the observable universe than grains of sand on every beach and in every desert on Earth combined. Every single person on this planet effectively owns several dozen galaxies of their own. Not stars, galaxies, each containing billions of suns and, most likely, an even greater number of planets, and all of that is still only the visible portion. Let's try one more analogy to help the imagination reach these scales. Shrink the entire observable universe down to the size of Earth. At that scale, our own Milky Way, 100,000 light years across, becomes a circle about 10 meters wide, roughly the size of a classroom. The solar system, Oort cloud included, becomes smaller than a bacterium. Earth vanishes entirely, invisible under any microscope. It would be billions of times smaller than an atom. That's the ratio between our home and everything visible. Now flip the analogy. Shrink the observable universe down to the size of your city, and neighboring galaxies become grains of sand just a few centimeters apart. At that scale, it becomes clear that, unlike stars, galaxies are actually packed fairly close together and constantly collide and merge. Our own Milky Way has a merger waiting for it, too. In 4 to 5 billion years, it will collide with Andromeda. Because here comes the biggest plot twist of our journey. The observable universe is not the whole universe. It's merely a sphere around us, the region from which light has had time to reach us during the age of the cosmos. That sphere has no physical wall. It's a horizon, exactly like the horizon at sea, defined by where the observer stands, not by any actual edge of the world. An alien in a galaxy at the very edge of our visible range sits at the center of their own observable universe, half of which is off-limits to us. So what lies beyond that horizon? Almost certainly more of the same. Galaxies, stars, planets, the same physics. The only question is how far it keeps going. And here, science offers an answer that's genuinely breathtaking. Measuring the geometry of space using the faintest ripples in the cosmic microwave background, the oldest light in the universe, shows that our cosmos is, to extraordinary precision, flat. Not flat like a pancake, but flat in the geometric sense. Parallel lines never converge or diverge, and the angles of a triangle add up to exactly 180 degrees. Flat geometry leaves only two possibilities. Either the universe is infinite, or it's finite but so colossally large that its curvature is undetectable. Some estimates suggest the true universe must be at least hundreds of times larger than the observable one, possibly unimaginably larger still. In other words, everything we can see, all 2 trillion galaxies, might amount to less than a grain of sand compared to the whole. An infinite universe carries some genuinely dizzying implications. If space really is infinite and uniformly filled with matter following the same physical laws everywhere, then the number of possible atomic arrangements within any finite volume is limited, which means that given infinite space, every possible arrangement eventually repeats. Mathematically, this leads to a strange conclusion. Somewhere unimaginably far away, there exists a region that's an exact copy of ours. The same galaxy, the same planet, and possibly even the same reader finishing the same video right now. It sounds like science fiction, but it's a direct logical consequence of infinity combined with uniformity. No mysticism involved, just pure combinatorics. Of course, none of this can actually be verified. Any hypothetical duplicates lie far beyond our observable horizon, but the mere possibility is a reminder of how radical the conclusions hiding behind the modest word infinity can be. Let's add one last brushstroke to the picture. The universe isn't static, it's expanding and accelerating as it does, driven by the mysterious force we call dark energy. The discovery of that expansion is its own dramatic chapter in the history of science. In the late 1920s, that same Edwin Hubble, while measuring the distances and speeds of galaxies, stumbled on a startling pattern. Almost every galaxy was moving away from us, and the farther away a galaxy was, the faster it was receding. There was only one explanation. Space itself was expanding, and at some point in the past, the entire universe had been compressed into a single point. That observation gave birth to the Big Bang theory. Interestingly, even Einstein initially refused to accept a non-static universe, and artificially tweaked his own equations to keep the cosmos standing still. He later called it the greatest blunder of his career. Then, in the late 1990s, scientists discovered that this expansion is actually accelerating, a discovery that earned a Nobel Prize. Distant galaxies are racing away from us faster the farther away they are, and the most distant ones are receding faster than light itself. That doesn't violate relativity. The galaxies themselves aren't moving that fast. It's the space between us that's growing. But the consequence is a sobering one. Galaxies are one by one crossing an event horizon and disappearing from our reach forever. Every second, the universe permanently hides thousands more galaxies from us. Hundreds of billions of years from now, observers in our galaxy will see only a handful of nearby stellar islands floating in an ocean of empty space, with nothing left to hint at the splendor that Earth's telescopes once had access to. We're living in a golden age of cosmology, while the universe can still be read. And finally, the promised payoff of that idea about telescopes being time machines. If looking farther away means looking further into the past, then the most distant light we can see should also be the oldest light there is. And it is. From every direction in the sky, we receive the cosmic microwave background, light that set out on its journey just 380,000 years after the Big Bang, when the universe first became transparent. This is the farthest wall our eyes can reach, a snapshot of the infant universe, stretched across the entire sky. You've actually encountered this ancient light in person. Some of the static you'd see on an old analog TV screen between channels was caused by this very radiation. The echo of creation was hissing quietly in every living room. And between Andromeda and the cosmic microwave background lies an entire universe of distance records, constantly being broken. The James Webb Space Telescope, peering deep into the infrared, has spotted galaxies whose light has been traveling toward us for more than 13 billion years. We're seeing them as they were just a few 100 million years after the Big Bang, in the universe's infancy. These earliest galaxies turned out to be surprisingly bright and mature, one of the biggest puzzles in modern astronomy. The universe, it seems, built its first stellar cities faster than theory predicted. Each new record isn't just a farther point on a map. It's a window into an era when the universe was still figuring out how to be itself. To look at the edges of the observable universe is to read the opening pages of its biography. So, how big is the universe, really? Let's sum up our ladder. 40,000 kilometers around the Earth, 384,000 kilometers to the Moon, 150 million to the Sun, a light year to the edge of our home system, 4 light years to the nearest star, 100,000 light years across our galaxy, 2.5 million to our neighbor, Andromeda, 500 million for our Laniakea supercluster, 93 billion light years for the observable universe holding 2 trillion galaxies. And beyond that, space that may simply have no end at all. Every rung of this ladder outstrips the one before it by a factor of thousands or millions, and at every single rung, human imagination taps out. But human science keeps climbing. The honest scientific answer to this childlike question is this: at minimum, incomprehensibly large, and quite possibly infinite. And here's the caveat any real scientist has to add. This is only what we know today. The history of astronomy has shown over and over that every generation underestimated the true size of the universe. It's entirely possible that our current numbers will one day look touchingly modest to our descendants. Scales like these frighten some people, make them feel insignificant. But there's another way to look at it. Out of all these unthinkable expanses, out of trillions of galaxies and sextillions of stars, We know of exactly one place where matter arranged itself into beings capable of asking, how big is the universe? And then, step by step, actually finding the answer. Tiny creatures on a speck of dust orbiting an ordinary star manage to measure the cosmos from their own backyard all the way out to a horizon tens of billions of light years away. Perhaps the truest measure of greatness isn't size at all, but the capacity to comprehend it. And by that measure, a small blue dot called Earth isn't lost in the universe. It's what gives the universe its meaning.